Today we have a mixed format for our conference, and we issue very interesting day of conference, interesting topics, interesting discussion, and interesting presentation. It's my pleasure to invite for first plenary lecture our colleagues from Poland, from Wrocław University of Science and Technology, Dr. Jarosław Szugiel. It's our pleasure. Thank you very much, Jarosław, for your visit and participation in our conference. Jarosław Szugiel holds PhD degree in computer engineering and worked as associate professor of Department of Computer Engineering, Wrocław University of Science and Technology, Poland. His research interests include programmable hardware, computer graphics and simulation, hardware implementation of cryptographic algorithms, and also numerical methods in maintenance and reliability analysis. And also author of over 60 papers and monograph chapters in these fields. He is also active in organizing committee of the International Conference of Dependability of Computer Systems, the post-real CONEX, which is organized by department every year since 2006. I think before such conference was, but I still comment. Yes, I can add that it's a beautiful conference, as the concept. It's my pleasure to invite Dr. Jarosław Szugiel for his presentation, Challenges in FPGA Implementation of Cryptographic Algorithms, a case study of evolution in Blake hash function. Welcome, Jarosław.
Thank you very much, Professor. I should be connected right now. Everything is seen and heard, I hope.
Yes.
Thank you very much for this nice introduction. Let me, first of all, let me allow to make this presentation sitting, because in this way I will be seen through the camera to everybody online. So before I start, let me invite you all to our conference. As Professor Kaczenko has already said, we have our series of conferences, DEPCO through COMEX. Next year, at the beginning of July, we will be celebrating, we can say, 20th edition of this conference. It is held in Brunów Palace, about 100 kilometers out of Wrocław, but we provide bus transportation, we provide all accommodation, full meals, social programs, so we take care of the participants throughout all these days. So you are cordially invited. If you need some info, you can also ask Professor Kaczenko, who is our honorable guest. Okay, now let's go back to my presentation. I will talk about, first of all, a few words about Blake algorithm, because this is a case study of FPGA implementation of this particular hash function. And then I will concentrate on two issues which arise in those implementations: size problems and power consumption. So it will be a very practical approach. It will be a case study. What are the challenges a designer may face when he or she tries to implement a cryptographic algorithm in hardware in general and in FPGA device in particular? So a brief introduction, because this is not a cryptologist conference. Hash functions are very common in computer science. In general, hash function takes message of n length n and produces so-called digest or hash, simply hash value, which identifies this message. And in cryptography, we have particular application because in general, hash functions are used, for example, for data organization, data structures, hashing tables. But in cryptography, we want to have the hash function difficult to be broken. Okay, so for any specific hash, it should be very difficult, it should be practically impossible to find a message which produces such a hash value. This is a pre-image task. On the other hand, having one message M1, it should be very difficult to find another message M2, such that we have identical hashes of both those messages. Of course, the hashes in cryptography are long. They are very big values, for example, 265 bits or half kilobits or even more. Hashes are ubiquitous in cryptography, actually. They can be found in any cryptography message, in message authentication, data identification, in digital watermarking. Actually, from good hash functions, good hash function, you can make a symmetric block cipher, stream cipher, whatever. So hashes has been, first methods have been introduced very early. Mr. Ronald Rivers from MIT proposed so-called message digest algorithms already in the 80s, and they create the foundation for first recommendations of Internet Society, so-called MD245 methods, which were published in these years, 89, 92, and soon there was an official SHA-1 standard. SHA stands for Secure Hash Algorithm, which was based on Mr. Rivers' developments. This first standard was slightly amended, extended in 2002, but it was obsolete by this year. And in 2007, National Institute of Standards and Technology announced an open contest for SHA-3, the contemporary, modern, and strong enough hash algorithm. There were 5 finalists. Alphabetically, the first one was our Blake algorithm. It was not a winner of this competition. Okay, sorry. So in 2012, actually Ketchak was announced as the winner. Some problems with microphones, too many microphones. We have too many microphones here.
Okay. It's necessary to disable sound of not the microphone.
Sorry for these technical problems. So the winner of the contest was another algorithm, Ketchak. I will make some comparisons here. But the Blake was and is still quite popular because it is very fast in software. It is significantly faster than Ketchak. And actually, cryptographers, those dealing with software implementations, do not like SHA-3 standard because it is slow. It is very strong. It is very safe and secure, but in software, it is slow. Blake is much faster, and therefore it is used, for example, in archive formats, in Linux kernel. You can find in key derivation functions, etc., etc. So this is not a dead project, although it originated a long time ago, and it was not a winner of the contest. In 2013, the authors proposed the second version, Blake 2, and 2020, quite recently, the latest modification, Blake 3, appeared. So it's still used and it is still alive. Okay, briefly about the structure of this algorithm, because we will be implementing this in hardware. The message first is divided into half kilobit blocks, and each block is first hashed, and then the result of the hashes is used as the input for the next block hashing. So this is typical chain sequential hashing, nothing specific here. But the essence of the method is this compress function. This is where the actual hashing is done, and implementation of this compress function is the subject of my work. I will present FPGA implementation of this compress function without talking about the infrastructure which is around. It is of secondary importance. The compression function consists of 14 rounds. This is also a typical approach in any cryptographic algorithm. We define one round as a set of transformation, and we repeat this round as many times as is needed for sufficient cryptographic strength. In Blake, we have state. This is a path of the so-called state bits, which is half kilobit, 512 bits. The state is composed of, this is the input hash value, and two other parameters, this is a salt and counter, these are secondary. But first of all, we have input hash value. This is the same as here. And this is the path of the state. The state goes through 14 rounds in sequence. The rounds are identical, but also the rounds use the message. Okay, so this is the message which is loaded as a second input to the compression function. And this message constitutes a parallel path of data, which must be provided to all round instances. This is a block diagram of Blake processing, and actually this could be treated as one implementation of this algorithm in hardware. We just make instances of all rounds in hardware, but this is a very expensive approach because we need a lot of silicon for 14 instances of the round. So in general, as a side remark, round-based ciphers are common in cryptography, and in general, we can implement them in hardware, first of all, in typical iterative architecture, which will be denoted as X1 here. We implement in the hardware in silicon just one round, and the state goes through the round as many times as there are rounds. In our case of Blake, 14 clock cycles, 14 times the message, and the state must go through the round. This is a standard iterative, the simplest approach, just like in the software. In software, we never repeat the same code of round 14 times or whatever times, one after another. We organize simple loop. In hardware, we can implement this standard iterative approach, but also we can unroll the loop, for example, placing k instances of rounds in hardware, and we need less clock cycles to complete the compression. And another technique is pipelining, where we introduce registers between parts of combinational paths. We split the combinational paths into pipeline segments. In this way, we load multiple parallel streams of data to those registers, and we have parallel processing. This is the fundamental benefit of pipelining. We increase the throughput because we process many chunks of data parallel concurrently, and we increase the throughput. This is how those architecture will be denoted here. If we have standard iterative with pipelining architecture, we will omit this X1 symbol. Okay, now let's return to the Blake round. The round itself is quite regular in Blake. It consists of 8 instances of so-called G function. The G function is finally the lowest level part of the algorithm. The state consists of 16 32-bit words because we have 512 half kilobits, so 16 32-bit words. 4 bits go to each instance. We need 4 G function in parallel processing the state for the first time, and in the same round after just reordering of the second processing in the second set. So we have 8 G functions in each round. And this is the last bit of definition of the cipher. Each G function is defined in the specification as a set of these equations. It's defined algebraically. This is a sequence of operation which should be done on the 4 input words VA up to VD. And when we transform these equations into data paths, which is something found in the hardware, in the silicon later, we get this diagram, something like this. What are the elementary transformations in this cipher? This cipher uses extensively additions. This is 32-bit addition. We take two vectors, add them arithmetically. We ignore carry out. Carry out is unimportant here. We just add these two vectors. We also have XOR, bitwise XOR operation. We take two vectors and XOR bit by bit. This is simpler than addition because we do not have carry propagation. It's faster and simpler. We also have some constants, okay? These are state messages, state words, sorry, M, these are message words. C, these are constants defined in the standard. And also we have the last third elementary transformation, we have rotations by a constant number of bits. We have 32-bit vector, we rotate it to the right by 16, 12, 8, or 7 bits. And all these operations constitute in silicon one instance of a G function, okay? Oh, I don't know. This is not here. Is it all? One point which is worth noting here, message words are taken in specific permutations. Sigma is a permutation defined in the standard, in the specification. In each round, we take different permutation of the words, message words, which are loaded here. Okay, what was the evolution?
Sorry.
In message path initialization, etc., which are unimportant for us. In Blake 3 in 2020, they first of all replaced the simple sequential chain hashing with tree hashing, which is very important for parallel processing of chunks of the message of the long file. For example, we divide it into 3 nodes, and then we can hash them in parallel. But it is also out of the compression function. Then the number of runs was further reduced to 7. But what is actually very important for us, permutations were removed from specifications. So here we see, here in this place, we see just a constant number of, as an index of the message instead of permutation. In place of the permutation, the message words are permuted after each round. So instead of permuting the words at the inputs of the G functions, we permute them out of the G functions after each round. And some other minor simplifications. Okay, so this is in brief presentation of the algorithm. Now, I made a sequence of papers about problems which arise in hardware implementations of these methods. What's the problem with message distribution in Blake 2 first? Then we will turn our attention to Blake 3. In Blake 2, first of all, most of the hashes, other hashes, including SHA-3 standard Ketchak, do not require separate path for the message. The message in virtually all other algorithms is loaded as an input to the round at the beginning, and then it can be discarded, it can be forgotten. In Blake, we need to remember the message because each round will use the message. In pipelining, it creates additional problems because we have to add additional registers, we have to divide the message path also to the pipeline stages we must synchronize. So this is a little bit complex. But the biggest problem is with these permutations, sigma permutations of the words, because all the message words which goes into the round must be selected dynamically at the input of the G functions, depending on the round number, depending on the specific permutation. In hardware, this means that we must implement 16:1 multiplexers, because we have 16 words on the input, just one output. All these signals are 32-bit signals. In all the round, we need 16 multiplexers, and their combined input is 8 kilobits. So we have half kilobit of data here, half kilobit of data here. This is the size of this hardware. And total width of those multiplexers is 8 kilobit. So this is a lot of hardware. Just to implement such a detail of the specification, multiplexing of the words, permuting the words dynamically inside the round. For each round number, we must use different permutation. Because this is dynamic permutation, then we have to use all those multiplexers. Already in 2017, I didn't like these multiplexers, so I had some thoughts that maybe it will be better to replace those multiplexers, for example, with dual block RAM memories, which are available in FPGA devices. Instead of those multiplexers, we need to load all message words into this RAM. So this is costly, it costs time. We need extra initialization time. But later on, we do not have any multiplexers. We remove those multiplexers at all, and we just address this RAM. Dual block port memories, it was a very fortunate coincidence because in FPGAs we have dual port RAM, so we can address the same RAM block with 2 outputs, not 3, not 4, but 2. And this is exactly what is needed for this application. So this is very fortunate coincidence, because without dual port functionality, we will not be able to use this approach. This is rather academic discussion, because in practical applications, I think no one would allow for this extra clock ticks for loading the memory with data. It is possible if speed is not our problem, but it is a little bit strange approach. It is rather academic consideration. But the results were simply, I was very amazed even by the effects, because the size of these modified implementations were reduced by half compared to the original approach. So it turned out that this one detail of the specification, that we have to multiplex dynamically words in each round, it costs half of the hardware in implementation of the method. This graph presents in percent sizes expressed in lookup tables. These are function generators in FPGAs. So this is a good measure of how many function generators in FPGA we need for implementation of the message. And as we can see in Blake, we reduce them to about 50%. In Blake 2, we reduce them even further to 45%, let's say. So this is, the reduction is over twofold. So the cryptographers came up with such a nice algorithm defined in all those equations, and it turned out that the message multiplexer, which was required in those equations, costed half of the hardware. If we remove it, we get such a big improvement. Actually, there was also some improvement in clock period, but it was not as spectacular. But obviously, when you have a smaller hardware, we have also faster hardware. So the reductions were up to 20%, let's say, in clock period. So we also get faster hardware. Okay, so after introduction of Blake 3, I was very, let's say, happy to see that in their specification, they removed those multiplexers. Instead, each G function gets the same 2 consecutive message words. We do not have those multiplexing. We have constant connections between message words and the functions, the modules. Instead, as it was noted, we must change the order of the words between each round, but this is just a permutation. Permutation in hardware is actually for free because we do it exclusively in routing. We change the roots of the signals and that's it. So permutation does not need any logic resources, any functions, generators, lookup tables, LUTs. And as expected, it also resulted in high reductions in size, but now we are talking just about regular implementation. Blake 3 versus Blake 2 is 32% smaller, a little bit less than half, but still it is smaller, and about 15% faster. This graph also compares the size and speed against catch-up, against SHA-3 standard. On the left-hand side, we have clock period, so the lower the better, the faster. In the right-hand side, we have size. And here we can see that the catch-up was quite large in hardware. It was larger than original Blake 2, and now it is much larger than Blake 3. But as far as speed is concerned, the catch-up is very fast in hardware. It has very efficient hardware implementation because we have very short clock periods. Now the differences with Blake 3, now the difference is a little bit less. So now finally we can say that Blake 3 is still much slower than SHA-3, but at least it is by 50% roughly smaller. So this is some sort of advantage. Okay, let me move on to, let me move to the last point of my presentation, power analysis. I will be talking here about pipelined architectures of Blake 3, because we are talking about speed here, first of all. And I will compare it with Blake 2 and Ketchak, but in the standard iterative organization. So these 3 actually are comparable among themselves. These architectures, this is extra case of high throughput Blake 3 implementations. When I looked at the power parameters, this was another surprise for me, apart from those sizes, because it turned out that the Blake is very power-hungry method, very power-hungry method compared to Ketchak, period. Here, no other comparison is done. The left-hand graph presents proportionality factor, because in contemporary CMOS devices, we have almost linear dependency between clock frequency and power. And this parameter is just a proportionality factor, milliwatts per megahertz. The second right-hand side parameter is better for comparison because it tells you about cryptographic cost. This parameter is total energy consumed by single hash calculation. If we have this proportionality, if the power is connected linearly with clock frequency, then we, knowing how many clock cycles are needed for single hash computation, we can also compute this metric, EH. It is microjoules per single hash. And here we can compare everything. First of all, please note that this is logarithmic scale, because the distribution is so wide that in linear scale we will not see much in this graph, because the first value for unpipelined, for purely iterative architectures, the parameters are very high. 250 down to 10 milliwatts per megahertz in P2 architecture. So we can see that Blake-free variants demonstrate huge power reductions with pipelining. When we switch from X1, from iterative unpipelined architecture to the 2 stages of pipeline, we reduce the power to 4.5%. This is 20 times the reduction of power. When we divide the logic into further pipeline stages, more pipeline stages, when we move from P2 to P4, we reduce the power to 28% and then to 76%. So obviously, there's a saturation with the pipeline length. But first of all, the X1 organization unpipelined is very power hungry, is very power inefficient. In Ketchak, we have this parameter 0.2. So this is, let's say, 5 times or even more. But this is mainly, because Ketchak requires much more rounds. If we compare this parameter, this characteristic, these values, we can see about 20. The difference between raw power consumption depending just on clock speed. Okay, so pipelining turns out to be a method of power reduction as a side effect, and this is well-known effect in digital hardware. First of all, we apply pipelining to increase the throughput, the speed of data transformations, but as a side effect, pipelining quite often reduces power because it reduces number of transitions per clock periods in signals. In the ideal operation, when a digital circuit needs to compute a new value, we imagine that the, for example, single bit just turns from 0 to 1. It switches from 0 to 1, and that's it. But in real hardware, there's lots of sometimes. There are oscillations in those in the switching. So it goes from 0 to 1, back to 0, etc., 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 many times until the final value is stable. Those transients are called glitches, and they are typical to complex involved combinatorial circuits. In Blake, the number of glitches, the number of transitions per clock period is very high. Over 1,300 glitches in top 5% most active signals, because obviously in the design we have lots of signals, thousands, hundreds of thousands signals. If we look at those which are connected with actual hash computation, we select 5% of most active signals, and we average the number of transitions. These are the numbers of this graph. And as we can see, adding 2 stages of pipeline reduce this 1,300 to just 48 transitions per clock period. In Ketchak, we have just 10 transitions. So this is very nice behavior, very stable behavior, taking into account that we are talking about cryptography, so we have very complex combinatorial transformations. In Blake, we need four pipeline stages to get to the level of Ketchak SHA-3 standard. Having seen this result, I came with my last point of my presentation. This was actually the paper from this year, which I'm preparing to publish in a journal. What if we replace these summation circuits with dedicated others, which are in FPGA array in DSP slices? DSP slice is a resource located outside of the programmable array. So we have a FPGA array, the classic standard one, with logic cells, with lookup table generators, with flip-flops. And beside this array, we have, first of all, block memories and also DSP slices. DSP slices, as the name says, were created were made for digital signal processing. They are very efficient in fast computations of multiply and accumulate calculations. And these calculations are the foundation of all DSP algorithms. In Blake, we have two, in each G function instance, we have two free input others and two input others, as you can see. For our purposes, we need to configure DSP slice in a very trivial way because inside DSP slice, we have very complex pre-processing logic capable of scaling, of pre-adding, etc. This is all needed for DSP algorithms. But what we need actually is this arithmetic logic unit, which can be programmed into a number of functions. We need just addition. And this all is done on 38-bit. We need just 32 bits for Blake words. So we do not use all this complex logic. We just use others. And we configure two input other or free input other by joining into cascade to adjacent DSP slices. In total, we need 48 DSP elements for one Blake round. This is a substantial amount. If we look at the changes in size and speed with DSP elements, this is the graph which shows those changes. As we can see, first of all, we see very high reductions in lookup tables in function generators by minus 33, 37%. Obviously, because now lookup tables are not used for summations, the others are in the DSP elements. But what we see is that there is no reduction in slices, actually. Slight increases we can see. Slices are the nodes of the programmable array. Every slice
Sorry?
Okay, so it's backward.
Mm-hmm.
Now it's stopped again. No, you have stopped again the sharing. You have to share
Really?
again.
Okay. What was that? Okay. Okay.
Okay, now it's okay.
Am I back
Yes,
online?
You can see, yes.
Yes, please continue.
Okay, so the question is, how many slides did you miss? Sorry. Okay, so on this slide, I was talking about the reductions which were made by application of DSP elements. The reductions is lookup tables, but deterioration of Fmax. And this slide was about the reductions, very good reductions in signal glitches. And this slide summarizes the effects of the application of DSP elements. As we can see, we have very efficient and nice reduction in power per energy per hash value in these two first architectures, but But in case of pipeline architecture, we do not any improvement. Instead, we see deterioration. This is because DSP elements are quite power hungry. They dissipate a lot of power. And if this extra power is too high, then we do not see any improvement. This is clearly seen in this chart because it shows that the logic component, which includes DSP, in highly pipelined organization is actually higher than the original one without DSP slices. This is the effect of high power demand of DSP slices. DSP slices are optimized for speed of computation, first of all, not for low power consumption. Okay, to conclude, because it's time for conclusions. This was a case study. Cryptographic algorithms are very specific algorithms. They have very involved, complicated internal structure. And their hardware implementation is always a problem because you get a very complex gate network which must be efficiently routed, etc., etc. In Blake 2, first of all, there were problems with specific message distribution. This was just one of the features in specification, but it had very bad consequences for size. Much better approach was introduced in Blake 3. But on the other hand, the Blake transformations are built on 32-bit adders, summation circuits. And these introduce a lot of glitches. They were introduced for cryptographic avalanche. Avalanche effect is very good for cryptographic strength, but it was a nightmare for signal stability and power consumption. Pipelining turned out to be obligatory just for power reduction, not for increasing the throughput, not necessarily, but just for power reduction. Or you can use also dedicated DSP slices as an alternative in unpipelined cases, at least, because in pipelined cases, there's no point in using DSP slices. This would be the summary of my presentation, but actually there's one important question, because I was not talking about cryptology, about cryptography. The basic question here is how to assess the cryptographic merit of all those modifications which were introduced in the cipher. Because we know that some solutions are very costly in hardware, we can replace them with our solution by introducing modification, but how does it change the strength of the cipher? This is the basic question. But the problem is that even cryptologists cannot agree about how to evaluate, how to assess cryptographic strength of specific algorithm, or specific parts of the algorithm. There are ongoing discussion which approach is better. There's no strict benchmark, let's say, which would allow to evaluate those parameters. And there's lots of discussion. At the end of discussion, the experts must vote because they cannot agree in any formal way. So this question remains open, but it is out of the scope of my presentation. Thank you. This will be all.
Thank you. Now we have short time for the question and answer. Let's start with our question online. Artem Pereplisov, welcome.
Thank you for your really interesting report, and it's fantastic and extremely interesting for me because it's exactly that I'm doing and I did and implemented. So it's really interesting to see the Blake 2 and the usage of DSP and the power analysis. But there are a few questions and comments, if you will allow. The first one is you considered the round-based implementation of cryptographic algorithms and considered the possibility of pipelining and some standard implementation like it was in software. But did you consider the mixed version while it's possible to pipeline some part of the catch-up algorithm and at the same time to create some number of instances to balance it inside the FPGA? I mean, to balance the resources. For example, if we need to obtain the result of catch-up computations during 15 clock cycles, it's possible to use some number of pipeline rounds. If less, it's possible to add more, and so on. So the question: did you consider the possibility of mixing round-based pipelining and direct parallel implementation? This is the first question.
Okay, thank you very much for this question. It's an interesting topic. No, I have not done any studies, not yet, about this mixed approach. But you are perfectly right. If we can see that something is good in unpipelined way and something is good in pipeline, we can try to mix. I haven't tried this, but it could be an interesting direction for optimizations. Yes.
Thank you. It's interesting because it allows to parameterize the resources. So depending on the available resources and requires to intensity of results, it's possible to use different combinations without a redesign of the code. Another question. You provided the possibility of optimization with DSP blocks. I assume that you are using Xilinx ultra-scale chips because of 48 bits of DSP. And they provide an ability to use 3 input adders based on single DSP slice because it's possible to use the carry input, parallel carry input, and it's possible to obtain 3 in adders.
But these others but these others must operate on 32-bit arguments. I think the path you are talking about is not this wide.
It's necessary to check it because it was already implemented in this way. And it's also interesting that it's possible to use such 48-bit DSP blocks to implement also XOR operations, wide XOR, and multiplexers if it's necessary to reach the dramatic fast computations. And this is the last question. You provided information about the power consumption dependent on the frequency, but you not specify the exact frequencies that were used and the amount of the resources per crystal. I mean the percentage. It's also interesting because the power consumption also depends on the percent of the usage of all the resources of exact chip. So maybe it's necessary to take it into account. I mean, add the information about the exact frequency. What is it? 200 megahertz, 300s, or up to 500s, theoretically possible. So it's really interesting to realize the exact results of the power consumption.
Okay, I didn't include all the details in my presentation, of course, but if you are interested, I have a full reports which are provided in the bibliography of my paper. In my paper, I can't remember, maybe I didn't include specific results regarding maximum. There's a table in my paper which will be published, I think. So you will see in the table maximal frequencies of all those architectures. If you are even more interested, you can look into my bibliography positions. What you are talking about DSP elements, Yes, of course, it will be another interesting direction for further optimization. You can also use DSP elements for different operations. Yes, but my point first, as the first step of the study, was to just compare the previous approach with this approach, which could be further optimized. Yes.
Thank you. Really interesting, and I think that it's necessary to check your publication. Thank you.
Yes.
Thank you so much. Sorry, we had not enough time for continue the discussion. Thank you, Dr. Yaroslav, for your.
Thank you once again for inviting me. This was a pleasure. Thank you.
Thank you. Okay, let's continue our plenary session, and it's my pleasure to invite for next keynote lecture.